So yeah, we're going to finally prove the regularity lemma. Just reminding you of a bit of notation and terminology. So the mean square, so this was like this, yeah, so E of xy, right, counts edges between x and y. Whenever we compute these densities or these quantities, let's just implicitly assume these sets are disjoint, right? Because I don't really know how to count it. I mean, okay, if they have some overlap, you have to decide how to count the edges in the overlap. So these are disjoint sets, not empty. So the mean square density of a partition, let's say x1 up to xt of the vertices of some graph is, so you take the sum over all pairs of partition classes where they're distinct, and then you compute the density between them, dxi xj squared, times the size of xi times the size of xj all over n squared. Okay. Oh, and if P is the partition, then we're going to write this by f of P. Okay. You might wonder where this word mean square density comes from. In some sense, this quantity is some sort of an average of the square of the density between, like if you take two parts, right? This is the square of the density between the two parts. And it's some kind of an average. Like basically, imagine I pick two vertices at random. And I have a random variable where, so if I pick two vertices at random from the graph, if they're in the same part, that random variable just gives output 0. If they're in different parts, I output the square of the density between those two parts. This would be the mean of that random variable. So that's why it's kind of mean square density. It's like pick two vertices. If they're in different parts, take the square of the densities between the parts. And this would be the average of that random variable. But anyway, it doesn't really matter. But that's just where this word comes from. Okay, so let's, one kind of cool thing about this quantity, it's quite useful because, so a very useful property is that if I take a partition and I refine it, so imagine I've got a partition, I chop up each part into smaller parts, the mean square density always goes up. Well, it doesn't go down. It's at least as large as it was before. So let's prove a sort of lemma that's going to imply that. So let A and B be disjoint sets. Suppose I take a partition. So I'm thinking of A and B as being two sets in a regularity partition or something. And we're going to refine the partition. So I'm going to break A into many, many pieces and break B into many, many pieces. And we want to see how the contribution of A and B to this kind of sum would change. So I'm going to take a partition A1, A2 up to AS of A. And let's say B1 up to BT is a partition. So I'm going to let this be a partition of A and this be a partition of B. then so if A and B were parts in some partition of some graph G, of course these are disjoint sets of vertices in a graph or something. The contribution to this sum from the pair AB, if we kind of ignore the n squared, because I mean this doesn't change if I change the partition. So the kind of contribution would be like the density between A and B squared times the size of A times the size of B. If we replaced A and B by this kind of refinement of A and B, so I want to compare the contribution of this kind of finer partition versus the original one. So I want to say that DAB squared times the size of A times the size of B, which if A and B were part of my regularity partition, that would be their contribution to this sum if we ignore the n squared. And I want to say this is at most the sum from I equals 1 to S, the sum j equals 1 to T of the density between AI and Bj squared times the size of AI and the size of Bj. Okay. So essentially, if I took A and B and replaced them with A went up to AS and B went up to BT, the contribution to this sum, this mean square density, could only go up. It could not go down, right? That's basically what this is saying. Okay, so let's prove this. Okay, so like a lot of things in this course, it's going to come down to two things: double counting and some kind of convexity inequality. So let's do some double counting. I'm going to count the edges between A and B. Well, I mean, if you think about it, that's the same as counting edges from like, A1 to B1. Like each edge goes from some, like, AS to B2. Like, it's the same as counting edges between the pairs of things in the partition classes. So this is like the sum I equals 1 to S, the sum j equals 1 to T of the number of edges between AI and Bj. Because these are partitions of A and B. Which I can say is, I'm just going to re-express this in terms of the density function thing by kind of moving this stuff over, right? So it's the sum I equals 1 to S, j equals 1 to T of the density between AI and Bj times AI, size of AI, size of Bj. So hopefully nothing too controversial so far, I think. So, okay, for reasons that will become clear later, let's square this. So I'm just going to take what I have at the first thing and the last thing I've derived here and just square them both. Okay. Remember there's like one common thing that we usually do is we start with like some kind of sum of squares, and then we lower bound it by a square of a sum. This is like a square of a sum, right? So we can upper bound it by some kind of sum of squares. But actually, we're going to, it's not going to be quite like that. We're not, I mean, the natural thing to upper bound this is, well, yeah. We're actually going to use the Holder's inequality kind of more carefully here. So I'm going to define some variables. So define, like for each I and j, define xij to be the square root of the size of ai, the size of bj. So just a number. And yij, let's make that like the rest of what's here. Like imagine I want to write this as xij, yij. So my xij is like the square root of this, and then the yij is going to be everything left over. So it's the density between ai and bj times the square root of the sizes of the sets. May not be necessarily clear why we want to do this, but when you apply Holder's inequality, it will become clear why this is the right thing to do. So we can rewrite the sum. So this is equal to I equals 1 to sum I equals 1 to s, j equals 1 to t. I'm going to write it like this, that it's like the absolute value of xij times yij. We don't really need the absolute value because these things are both positive, but just to make it clear how we're applying Holder's inequality, I'll just write the absolute values. So yeah, if you look in the appendix or you look back to some notes for something from way at the beginning of the course, if you have a sum like this squared, I can bound that above by the sum. So again, I equals 1 to s, j equals 1 to t. I can kind of, in some sense, I can kind of split these and square each of them. So it's like xij squared, and then yij squared. And then these sums are not squared. Like this, you have a square over here, and then the squared kind of goes inside, and you have a product like this. Okay. You could think of this as being an instance of Holder's inequality that we proved a long time ago when we were doing convexity. Or you could think of this as the Cauchy-Schwarz inequality. What is this? This is like if I take a vector where each entry is xij, and there's like s times t entries, this is the dot product of that vector with itself. This is the dot product of vector with the y's in the entries with itself. And this is like the dot product of the x with the y's. So Cauchy-Schwarz says, like, if I have any vectors, if I dot product them and square it, it's at most dot producting each of the vectors with themselves and multiplying. So that's another way of thinking of this. And just think of a vector here where these are the entries of the vector. You would get the sum of the squares like this, and yeah. Questions about this bit? Okay. So then we can just plug in what xij and yij were, and it's going to work out nicely. So we've got that this is at most so when you square the xij, it just gives you this size of a times the size of b.
Is there still a square in the EAB?
Oh yeah, totally. Yeah, thanks. That's probably quite important. And then the other term becomes, it's the sum of the densities. So it's the same double sum as always, and then you take the densities ai to bj squared, size of ai, size of bj. So sorry, it's getting a bit cramped on the side of the board. But yeah, this just plug in what yij is and square it. And then the nice thing is that this sum here just counts the size of A times the size of B. Because if you think about it, yeah, each AI and, it's the size of A times the size of B by, I guess, collecting terms and whatnot. You can kind of, bring one of these sums inside, and then it gives you size of B, and then, size of A. And then, well, I mean, this thing is just kind of this thing that we wanted to prove something about, basically. If we divide both sides, so I've got this is at most this. So divide both sides by the size of A times the size of B. And if you think about it, what is EAB squared times the size, divided by the size of A and the size of B? It actually is equal to the size of A times the size of B times the density between A and B squared. If you think about it, it basically, these do compute the same thing. So we get that this is at most this sum, which is exactly what we wanted to prove. So the kind of message of this is, if you refine a partition, if I take a partition and I chop up each thing into smaller things, the mean square density never goes down. It can only go up, right? Because it's essentially, when you chop things up, you're essentially replacing a term like this with like a bunch of things like this, and that only goes up. So kind of a corollary of this lemma is that if I have two partitions where P prime refines P, then F of P is at most F of P prime. Okay. Oh, one thing I probably should have mentioned before, but I think we talked about it last time, is that this mean square density of a partition is always bounded between 0 and 1. And what we want to do is kind of take our partition, refine it, and increase the mean square density. And it can't go above 1, so that's going to be kind of important. But yeah, basically, what this is saying is that if we take a partition we've got and just refine it, we're never going to be going backwards. Like, we're never going to be losing mean square density by refining. It can go up, but it can't go down. So I'm not going to prove this, by the way, because this is an exercise that I think you guys don't have this in your assignment this year, but sometimes I like to use it. So yeah, we're not going to prove it. But this is actually fairly easy to prove just from the definition and playing around with it. So yeah, your mean square density is at most 1. Okay, so what I want to do next is, what we kind of want to show is that not only if you refine a partition, not only does the mean square density not go down, but we want to say if you had lots of non-epsilon regular pairs, and I refine to kind of expose those non-epsilon regular pairs, then my mean square density is going to go strictly higher by some measurable amount, some like large quantity. Or maybe not large, but something I can control. So here's a lemma. So let A and B be disjoint sets. And we're going to just think about splitting A into two sets and B into two sets. So suppose like A is the disjoint union of A1 and A2, and B is, let's say, the disjoint union of B1 and B2. So what I want to show is that so again, we're going to look at this kind of quantity. Now kind of it's like S is 2 and T is 2 kind of, but otherwise it's similar to what we had before. So this sum we want to show is at least the size of A times the size of B, DAB squared. This is what we had before. But we want to have an extra thing to say that it gets sort of boosted up by dA1 B1 minus DAB all squared times A1, size of A1 times the size of B1. Okay. So the relevance of this is that, like what this basically says is if there's a big deviation between the density between A1 and B1 and the density between A and B, like this is a square, right? So if there's any kind of difference between these densities, this is going to make it positive, right, by squaring it. And you're going to have like a sort of, you're going to be boosting basically, you're going to replace your mean square density from, one of the terms will change from this to this, which will be boosted by this amount that we can kind of measure, right? Like it's going to be some epsilon, something involving epsilon and stuff like that. If it's not epsilon regular, right? You would use A1, B1 to be a certificate that it's not epsilon regular, and this is going to, be large, kind of, or be something that you can control. Okay, let's prove this. It's not too different from what we just did. We're just going to keep a bit more track of things. So let me start by just writing out, so I'm just going to write, let's say, size of A1, size of B1, density between A1, B1, minus density between A and B, squared. Okay, so I'm just starting with this thing that I want to prove is like this amount I'm boosting by. So, so of course, this is at most if I was to sum over all I from 1 to 2, j from 1 to 2, and take ai, bj, and a kind of analogous quantity here. So d ai bj minus dab squared. Okay, the reason this inequality is true is because, well, I mean, this term appears in this sum when I is 1 and j is 1. And then there's 3 more terms in this sum, all of which are non-negative, because squaring a number makes it non-negative. So is it clear how I go from here to here? Just the I equals 1, j equals 1 term is this one. Now I'm just summing over all of them. Okay. Now let's just expand this square and see what happens. So my first term will be AI bj density squared. Density between AI and bj squared. Then you've got like the awkward kind of middle term, which has a 2 in it, right? Again, well, actually, yeah, okay. I equals 1 to 2, j equals 1 to 2. Again, we have every term is going to have an AI and a bj. I've got density between AI, bj, and then the density between a and b. And then my last term, AI bj, density between a and b squared. Okay. Just some algebra. So in the second term and the third term, we've got these DABs, and those can just kind of come out, right? Because that doesn't depend on I and j. So this middle sum, well, so this term, take out the DAB, right? This is now just summing up the size of AI, the size of bj, and the density between them. But like just by the formula for what does this density mean? I mean, this is number of edges divided by these two quantities, right? So this is just count, like once I take this out, this is just counting how many, it's summing over I and j and counting how many edges are there from AI to bj. So all this computes is, so let's pull out the DAB. And actually, so if I sum over all I and j and I count edges between them, that just counts edges from A to B. So okay, so including the 2, let's say this is a 2 times DAB times the number of edges from A to B. Because again, it's counting edges between all of the different things, but that adds up to the number of edges between A and B. And actually, this last term is similar, weirdly enough. Factor out the DAB squared. And then all of this is going to do is it's going to compute the size of A times the size of B. But remember what the density is. It's the number of edges over a size of A, size of B. So like if I kind of bring that in there, I could cancel one of them. So that is just, again, DAB, EAB. So like these are kind of the same thing, except this one's has a -2 on it. size of A1, size of B1. So I'm just kind of repeating the left-hand side of this inequality. So DAB minus, oh, sorry, DA1 B1 minus DAB squared is at most, sum I equals 1 to 2, j equals 1 to 2, AI bj, density between AI and bj squared. And then, like I said, this minus 2 term is like minus 2 times this, and this positive term is the same thing. So it's just minus one of them. So like minus what's the best way to write this? So I'm gonna write this as size of A, size of, yeah, this makes sense. Size of A times size of B times DAB squared, which, remember, that is the same thing, right? So this last term is equal to this. The middle term is negative 2 times the same thing. But then I just move this to the other side, and it gives me exactly what I wanted to prove. Right. So just move to other side. Right, and that's exactly the correct inequality. Okay. Okay. So now we have everything we need to describe kind of the first. So, okay, the way this algorithm is going to go to get a regularity partition, you start with any regularity or any partition, arbitrary, into T parts. We now understand what we would do for like the first phase. So I want to like go from that partition to another slightly better partition. And the first thing you do is you kind of okay, that's fine. So basically the algorithm for getting a regularity partition, so start with, let's say P0, which is an arbitrary partition into T parts. T is some parameter in the regularity lemma, right? So where xi has size roughly, I mean, the ceiling, it's just the ceiling or floor of n over t. If this partition, if you just got lucky and it satisfies the criteria, you just output it, right? So so if P0, if P0 is good, meaning at most epsilon t squared of the pairs are epsilon regular, just output it. Otherwise, there are at least epsilon t squared pairs. Like the only thing that can go wrong is that there are lots of pairs xi, xj that are not epsilon regular. Okay. And basically what we're going to do is go through them one by one. And for each such pair, so let's say this pair is not epsilon regular, there is a certificate, meaning there is a there's a subset of xi and a subset of xj which certify that it's not epsilon regular. Right? Because being epsilon regular means for all subsets of a certain size, the density is between them is basically the same as the density between xi and xj. The negation of that is there exists a set here of size at least epsilon times the size of xi. There's a set here of size at least epsilon times the set of xj, where the density between these sets differs substantially from the density between xi and xj. So take that certificate and refine our partition by saying, okay, my new partition, I mean, from the perspective of these two parts, I'm just going to say, okay, cut xi into two sets, this one and the complement. Cut xj into two sets, this one and the complement. So each time I do this, we boost, your kind of, well, MSD, so mean square density, by how much? By whatever kind of this kind of quantity is. So in order for this to certify that it's not epsilon regular, this difference has to be at least epsilon in an absolute value. So I get like an epsilon squared here, right? Size of my little certificate set, well, it could be like epsilon times the size of xi. The other kind of certificate thing is like that. And all of my sets were about n over t. So this is roughly giving me a boost of like epsilon to the 4 times n over t squared. The mean squared density is supposed to be divided by n squared. So sorry, I should put an n squared, 1 over n squared everywhere. Because this quantity, like here we kind of omitted the 1 over n squared. So yeah, sorry, I'll put a 1 over n squared here. So the mean square density goes up by at least like epsilon to the 4 over t squared when I refine this pair. And then I go to another pair, which, I mean, it could be a totally disjoint pair. And then it's kind of clear what you do. You just keep refining it. Go to another pair that's not epsilon regular and refine it. Or it could also involve this one, but then I would just refine it like in this way. If you think about it, it's not, well, because refining things doesn't ruin the the gain in mean square density we've gained so far. It won't be ruined by this. So yeah, you just you would just kind of refine this further. And the thing is, there are at least epsilon t squared such kind of bad pairs. So on each of them, I gain something like this. So in total, I would gain something like, let's say, epsilon to the 4 over t squared. So I get this boost per non-epsilon regular pair. The number of non-epsilon regular pairs is at least epsilon t squared. The t squareds cancel. So I get like a boost of something like epsilon to the 5. And then if we're like careful with all these floors and ceilings, let's say it's epsilon to the 5 over 2, right? For just dealing with like, I don't know, floors and ceilings and stuff like that. We can throw away a factor of 2. Is it clear what I'm saying here? That for each non-epsilon regular pair, you boost epsilon to the 4 over t squared. There are epsilon t squared of them. So just do that epsilon t squared times, and it'll be like an epsilon to the 5. And if we want to be careful about floors and ceilings and stuff, maybe just throw away a factor of 2. It doesn't really matter. Questions about that? It's a little bit vague and hand wavy, but so this is what you use to go for. So you go from P naught, P0, to some partition. Let's call it Q1, where we boosted the mean square density by epsilon to the 5/2, let's say. But this Q will not have parts of the same size. Because, yeah, we didn't have any control over how big these certificates were. There's no way that they're going to be the same size. And especially when I refine things multiple times, this Venn diagram is going to have regions of different sizes. I can't control that. So then we have to do something where we chop things up and reorganize them. So because it was kind of important that all of these things had the same size initially, because we were kind of using this, that each of them have size n over t squared, or sorry, n over t. And that's when we refine, like in the next step, we're going to want this property to be satisfied again. So we do want the sets to have the same size. Okay, so here's a lemma that allows us to get the sets to have the same size. So for all, let's say, delta greater than 0, and partitions, let's say Q, so maybe we'll call it x1 up to xm. There exists a partition P, which I'll call like x1 prime up to xt prime, such that so first of all, I want to say that the number of parts in the new partition is not that much bigger than the old one. So let's say it's like 2 times m ceiling over delta. Okay, if delta is small, this is quite a lot bigger, but it's just a function of m and delta. I want every set in my new partition to have roughly the same size. So they're all of size n over t, or floor of n over t, ceiling or floor. And I want to say that I didn't lose very much. So the mean square density is at least what I had before minus delta. Okay, and this delta is something I could choose, right? So what we've done here is we've gained, like, let's say an epsilon to the 5/2 in mean square density, and I could set my delta to be like epsilon to the 5/4 and apply this lemma, and then you could say, okay, so I already gained epsilon to the 5/2, I lose epsilon 5/4, so I still in total gain epsilon to the 5/4, right? And now I've got that all my things have the same size. Okay. Let's just kind of roughly say how this goes. Although, actually, maybe I can just prove this whole thing. So here's the idea. Think about your partition Q. Now for each partition class, just do your best to split it up into sets of the right sizes. What do I mean by the right sizes? I mean n over t ceiling or n over t floor, right? Because we're trying to only use these two sizes in our new partition. So just do your best to do that. So start, I'll take a set of size, let's say ceiling of n over t here. And okay, now I'll take maybe another one of ceiling n over t. And then take one of the floor size, And of course, you're going to like end up maybe with some leftover stuff. Like once the number of things left is strictly less than n over t floor, then you can't keep going. So here I've got like a leftover set. Let's say this is x1. This is my leftover set y1. Yeah, of leftover vertices. And the size of y1 is less than n over t. And just keep doing that. Now, you do have to be a bit careful. So this would be my y2 of leftover stuff. So here's one thing. Don't use too many of size like. So you're only allowed to use these two sizes. And like, just do it in a sort of reasonable way that, I don't know. Like, let's say that the number of vertices is like, let's say, 1,000 t plus 1. What you would want to do at the end, what you want is exactly one set of the size being the ceiling and the rest being the floor. If you think about this case, right, this is like it's pretty much divisible by t, just one extra. So you would, like if you're doing this partition, you just don't use more than one of these. If n was like this, for example. So like if, let's say, the remainder when I divide by t is like r or something, don't use more than r of those, the big ones. And don't use too many of these either in some sense. Like if this was a -1, I would not use more than one of these, right? So just don't do anything that's going to screw everything up. But yeah, so use these two sizes and cover as much as you can, right? But still, like I think in every blob, you're going to get some leftover thing, which is, I mean, OK, it's certainly at most like this plus 1 or something. I mean, it's not much bigger than n over t, right? Because otherwise, I'd take either a floor or a ceiling from it, whatever one's appropriate. Does that make sense? OK, so my first step is I'm going to just say, OK, refine into this partition where you only use these two sizes plus leftovers. So refine Q as above as my first sort of step. And of course, the mean square density doesn't go down. Because that's just a rule. Like when you refine things, the mean square density never goes down. Okay, and then all we do is we say, OK, take all the leftover stuff, put it all in a big blob, and then chop it up into sets of the right size completely arbitrarily. So take my leftover stuff. So this is like the leftover stuff from x1, x2, up to xm. And chop it up into sets of size, floor of n over t, and ceiling of n over t, which you can do because we were careful in the first step, we didn't mess up the numbers. Like we didn't use too many of either size. Like this now it still can be partitioned into these sizes. And then to see how much you lose in the mean square density, you just have to say, OK, how much were these leftover things contributing before to the mean square density? Like of this refinement. And it wasn't very much. So the loss of mean square density is at most well, yeah, I don't know how enlightening this calculation is going to be, but what I should be computing here is like yi times the size of another part times the density between them, but that density at most could be 1. So I mean, essentially this is just, this is just computing kind of 2 over n times the sum of the sizes of these yi's, which is was 2m n over t basically, which is at most delta. Sorry, no, there should be another over n here. Anyway, let's not worry too much about this, but basically, when you refine, the mean square density doesn't go down. And then if I do this reorganizing and chopping up, the only thing you could lose is the contributions that you had from those yi's. And those things are small, so they weren't contributing that much. It's not a big deal. And so the most that you could lose is this delta. Okay. Any questions about any of that? Okay, so that basically, if you put all the pieces together, that proves the regularity lemma. And then, yeah, we'll do something else next time.